All right, the final speaker of today is Dr. Michael Kaminsky from Argonne National Lab.
Thank you, Mike. All right, Scott had mentioned that one of the risks to the public was resuspension. So resuspension is kicking up of radioactive material that has already been deposited onto the surfaces. And so that's been a subject of special interest to my graduate student who was my PhD student who recently graduated and got his PhD and now is working as a postdoc in my group, Nico Diega. And this is work that now is being funded by DHS and in collaboration with EPA and Matthew Magnuson. So Nico's, I should say that I'm giving this presentation for Nico because this is the subject of his doctoral dissertation, was the accurate measurement of the resuspension of fallout particles and its effect on the input into urban plume models. So there are a number of plume and dispersion models that describe particle resuspension, but there's a lack of experimental data that the modelers can use as input. So these models handle resuspension, and they handle them in a generic way and provide recommended values for these resuspension factors, they call them. But the modelers have no background, have little background in understanding what are good values depending on the situation. So we're particularly concerned with the emergency phase. So this is freshly deposited material. So fallout has just happened. It might have been hours before, weeks before, but in general, there has been little precipitation or any movement of the material in the environment. They can be deposited onto paved surfaces for emergency operations. So we have incoming vehicles, we have emergency operators operating, life-saving operations occurring, decisions on evacuation, on whether to evacuate or not. And those decisions are made based on risk to the public, and operations are based on risk to operators. So the ground is going to be disturbed by vehicle and pedestrian movement and activities. So we saw the opportunity to critically evaluate prior resuspension studies in the literature, and they've gone back to the late 1940s, early 1950s, a lot of studies. So we summarized the data on vehicle and pedestrian movement, and then recommended resuspension factors for very specific vehicle and pedestrian movement activities that can be used in existing models such as Turbo, Fermac, ResRad, and Quick. And then we identified gaps in our knowledge and then recommended experimental and theoretical opportunities. So this information is already been completed. So we've already submitted our paper to Health Physics. We're expecting them to notify us that it has been accepted after revision any day now. So that should be coming out in the next month or so. And this is kind of the summary of our analysis of resuspension factors and its potential effect on the public. So what we did was we ran ResRad, which looks at pathways for contamination in an environment. So this can be ingestion pathways, inhalation pathways, radioactive shine from surfaces. So your radioactivity like gamma rays are hitting you. And in these particular runs, we were concerned with resuspension off the surfaces. So we're ignoring ingestion because of food. We're really concerned with resuspension and then inhalation of those resuspended materials. And we're not going to look at that top right plot because you can't see it here. But if we look at the bottom two plots here, what we have is a dose limit of 1 millisievert, which is the maximum dose to the public. This is the left side is for cesium contamination on the ground, and then the right side is for americium-241 contamination on the ground. And then what ResRad calculates is the stay time, how many hours per year you can stay in that area that's experiencing a resuspension before incurring the maximum dose that we specified here as 1 millisievert. So this is for the public. And these various curves here and the colors are associated with the contamination on the ground. So if we look at the black 370 kilobecquerels per meter squared to the red dashed lines of 3,700 kilobecquerels per meter squared, this constituted hundreds of square miles for the Fukushima event. So this is not something that's very high levels of radioactivity that's very near the detonation or the release event. And so that's these two curves here. And what we see is that if we go to 10 to the minus 6, so this is the resuspension factor in the x-axis. So 10 to the minus 6 resuspension factor is the recommended value in ResRad and for the other models in Quick and Turbo Firmac. So if you have no information, you plug in 10 to the minus 6 because that's a typical value for resuspension. And I should say the 10 to the minus 6 is a ratio of the concentration on the ground and the concentration in the air. So if it's 10 to the minus 6, you're having a 10 to the minus 6 lower concentration in the air than you're experiencing on the ground. And there's a unit conversion that leads to 1/meters. But so 10 to the minus 6, that's just our default value. And what we see is when you run ResRad, it's right after you increase the resuspension factors beyond 10 to the minus 6 that you start to see it as a strong function on your stay time. And you can get from vehicle movement and pedestrian movement, you can get resuspension factors that vary from 10 to the minus 2 to 10 to the minus 6 based on the literature. And so you really need to know what that value is. And it's not hard to get away from 10 to the minus 6 to 10 to the minus 4, 10 to the minus 3. And so you start to see that your stay times can go from 100 hours to less than 10 hours, or from 10 hours to minutes. So this can really have a dramatic effect on you. And then if you look at americium here, it's even more of an effect. And Scott was alluding to that in, or no, directly mentioned that in his talk about how americium is particularly important because of the dose hazard associated with the alpha emitters. So in this plot on the right-hand side, even for the lowest contamination, there's a severe consequence to inputting a 10 to the minus 6 default value in these models, when realistically you might be much further down and have stay times that are less than a minute. So it's really could affect your ability to, or your decision making on, do we evacuate or do we not evacuate? Do we allow operators in, or what level of PPE protection is required for operators to be in those conditions? And that's going to affect your ability to operate for long periods of time. And so what Nico was particularly interested in then is experimentally being able to measure resuspension factors. So you're going to be looking at quantifying the amount of dust that's in the air after you've put dust down. And so there are standard equipment that's used. So the EPA uses for many instances these dust track models. So these are two different handheld models. This model here, or no, actually there's a separate model that's inside this ruggedized case, and it has been ruggedized for transport and movement around. One of the things that the company will tell you is that these units are calibrated for intake based on this unit configuration. And when you ruggedize the container, there's actually separate tubes that go in. There's a catch that's underneath. This is the actual intake. There's a catch here, and then you would have another probe up here to collect the air. These are not certified by the company to meet their calibration requirements. And so what we were finding was that these monitors, it seemed that their ability to measure heavier particles, or particles that were greater than 1 micrometer, 2 micrometer, that this might have compromised the ability of the units to measure those types of particles. Because they're bigger particles, they don't move in slow fluids without settling out. They'll settle out inside the catch, the tube catch that's located under here, or they'll settle out in the tubing and the turns in the tubing that are needed in order to direct that the air into the reading unit that's inside the case. So Nico wanted to look at different types of air monitoring systems. So this one here is a plant tower. In this case, it's a blue box, but it's a black box. The unit is embedded inside that system, but it does provide you with wiring to connect this unit. It's not a convenient unit. It's designed to, you plug it in with a Wi-Fi connection, you make the communication on the web, and that's your fixed location. You don't move it anywhere. If you want to move it, you have to reestablish a connection through the company, dictate where it's being moved, and then reestablish a connection. So it's not a very convenient unit. And so Nico developed and configured this board to connect to the plant tower through these connectors. It has a micro SD reader so that it transfers data. It operates on solar power and has a panel display so that we can see the readout in real time. In order to get the data out of the plant tower, you have to wait for the data to get collected. Then you log into the website, and then it provides you the data that has been collected. But you don't know whether the machine had stopped operating sometime during your collection period. So very inconvenient. But then we have a USB connector that we can drop this data off at any time. And so we ran in-lab comparison tests. So this is just a plexiglass box with fans operating. We would drop some dust material down. So we were using bentonite clay, which was filtered through 400 mesh, and then other silicon dioxide microparticles that were nominally 0.5 micrometer, 2 micrometer, and 15 micrometers in size. And so we were pulling air out of this box and running it through the dust tracks at the same time as we had his modified plant tower device embedded inside the box to collect. And what we found was not very good agreement in all the tests. And I just want to give you, I'm not going to show the disagreement between the two. That'll come up in the next slides. But this is typically what comes out of the unit. So this is the dust tracks, and it's showing you as you're collecting air into the unit as a function of time, what is the milligrams per meter cubed of material. So it's not necessarily counting particles. It is a laser device, so it's reflecting light off, and so you're getting diffraction patterns of light off of these particles. Based on the refractive index and the composition of these particles. And so you get a complex wave pattern. Usually the detector is at 90 degrees, but that can vary depending on the type of scattering event that you're really focusing on. But so you're getting this scattered pattern to the detector system. It's a very complicated wave pattern unless you really have monodispersed sizes. And so these units are calibrated then to a certain type of dust. So the dust tracks and many other systems are calibrated to Arizona road dust. And so they'll take the Arizona road dust into the laboratory. They'll dry it out. They'll run it through a very specialized aerosolizer to make sure that it is in discrete particles and aren't agglomerated. So these are very well conditioned and controlled operating conditions, unlike whichever you'd see in a laboratory in a field. And so then they have limited ability to modify the software's ability to interpret that incoming sensor signals and then attribute a size range to it and a particle concentration to it. So you can imagine there's not a single solution. This unit is trying its best based on the calibration to estimate these sizes. And so when they do comparative studies that are in well-controlled environments and they vary away from Arizona road dust, you can get a factor of 2, sometimes a factor of 10, sometimes much worse if you're really far different in material. Luckily, Arizona road dust is very good surrogate for urban dust. It's just the size range that's going to be really troublesome because humidity effects are going to change the size range. And what we found was that essentially, if we're reading very high levels of PM1, so less than 1 micrometer nominally, you are going to see also the PM2.5, the PM4, PM10. And then if these were low, then these become very low or below detection limits. And that's because of that scaling factor and the fitting factors that are used by the software to relate the incoming signals to an Arizona road dust-like material, which they know what the size distribution of Arizona road dust. So it assumes essentially that whatever's coming in is going to have a similar size distribution. And so that's why it can be assigning values of size where really it's not seeing that type of size. And so when we ran this is the dust tracks unit against the modified plant tower system. for a bentonite clay and the silicon dioxide that was being resuspended in that plexiglass box using the fans. We were getting a maximum resuspension factors of, say, 10 to the -4, far different than what we were seeing with the plant tower device. Now, granted, the plant tower device does a poorer job of seeing the larger particle sizes for a number of reasons. The limited limited capabilities of the laser and detection system on the plant tower device. It's like $30 for a plant tower. It's much cheaper than the $10,000 or about $10,000 for the dust tracks device. So it is much more limited. It also, the plant tower has about a factor of, I don't remember if it's a factor of 10. It might be a factor of 10 lower air intake rate. And so it's a much slower volume of air that's coming in. And so larger particles that have a much better opportunity to settle out before it's actually reached the detection system is what we suspect. And so the inaccuracies of the DRX and the plant tower are because of the sensors and the way the sensors relate the incoming signal to then a particle concentration and a size distribution of those particles. And most of it comes down to the way the mathematics works. And I'm not going to go into this in detail, but I just want to say this transfer function here. So it's going to be integrating the signal that's coming, or it's going to be, there's a signal that's coming in, and it's trying to figure out what the size distribution is or the particle, the number of particles as a function of that particular size. And it uses a transfer function to relate this to this incoming signal. And it's this transfer function is the proprietary nature of the software that's used by the company. And so that's the black box. And so we have no way of tapping into that to modify the transfer function unless you modify the unit and actually intake the raw signals and then do your own mathematics on it in order to back calculate out what the size concentration and the number concentrations are. So we wanted to learn, though, if we're going to do these in the field, because these experiments haven't been done in over 30 years. So Nicholson in 1989, and then before him, it was Semmel who really did the pioneering and the incredible job of doing data collection in the field. And so the purpose of these studies was to evaluate the experimental methods and design a template for future experiments, which we're now getting ready to start up. And so you'll see that we had the customized plant tower device here, and then here we're showing the dust tracks inside the ruggedized container. And so we used a residential roadway. I should say Nico and his team used a residential roadway, and then they planted the bentonite clay onto the surface using a couple of different techniques to spread it, and then drove the car over the surface. And so we did a control where we did not do anything to the road and just looked at whatever the ambient kick-up of dust was going to be, and then vacuumed the road off and looked to see if there was a difference in that ambient levels, and then finally seeded the rows as I showed there. And so since we, for the clean road and the dirty road, we didn't have a way of knowing what the initial concentration on the ground was. So we were just looking at relative resuspension factors and between the dust tracks and the plant tower device. And what we're seeing is that we're getting values of the relative resuspension factors that are different between the units. And this one was by far the most different. So we seeded the ground, and actually in one of the trials, the concentration that we're reading in the dust tracks is lower than when we didn't seed the ground, which doesn't make any sense. It does make sense if you think about that we had a small section of roadway, passed a car over it, not controlling where the air is moving. We have one device that's in a location that we think is downwindish, but when you have a car passing by, it's got a draft of air that passes behind it. So there's really no way of configuring your detection system where you can guarantee that you get a representative signal of the concentration that's in the air. Really, the way you'd want to do this is indoors, and you have the facility, you have the area tented out, and if you can control the way the car is drafting that material, you would then have fans inside that containment that move the air around so that you get a homogeneous concentration of air inside or particles inside that air, the control volume. And then you would have a better sense that whatever you're reading is a reading for the entire air volume. Because in order to calculate, the resuspension factor is such a crummy term. But they started using it back in the 1960s because they kind of threw their hands up and said, okay, this is really difficult. The physics, we just can't figure out the physics. It's way too tough. So let's just start hand waving and aggregating terms, and then you come up with a resuspension factor, which says, okay, if we have a concentration that we know on the ground, and then we have a homogeneous concentration that's in the air volume above it, then okay, that's kind of reasonable. That would be fine, and that's how the models are using it, because there really is not much better than that. Oh, and so one other thing is just then, so because we did the seed the ground and two separate experiments, we're able to develop maximum resuspension factors and average resuspension factors for vehicles passing. And they're 10 to the -7 to 10 to the -8. So this is 1 to 2 orders of magnitude lower than the default value that's used by these models of 10 to the -6. We think this is an artifact of just a poor setup experimentally. But I think the take-home message is these are not easy experiments to do. When Semmel was doing his experiments, he had a series of detectors that were lined up away from the roadway where he had a roadway that was seeded for a long period, a long distance. And then he had detectors that ran orthogonal from that roadway and also down the length of the roadway. And then he was collecting the data from all of these air monitors. They were filter based. And then doing an average of the volume of air that those detectors were contained in. And so that's how he was able to develop his values. There's other ways of doing it without going to those extremes, but I think what you end up doing is you end up becoming overly conservative in the amount of material that you think is resuspended. And so then if you're overly conservative, I don't know if that's any good either. So we're trying to find a happy spot in between where you don't need 25 to 30 detector systems and the dramatic costs associated with running a system like that, and trying to take advantage of these simpler air monitoring systems and just understanding what the limitations of those are, and then being able to compensate for those limitations. So in conclusion, from the literature, we were able to recommend several conditions, in fact, 5 conditions that we have some confidence in the resuspension factors that are reported in the literature. And so they are immediately available to modelers. And these conditions are a fresh roadway and a limited number of cars have passed. And then another one where many more cars have passed. And you can imagine what happens when you pass cars over a roadway that has dust on it. The dust gets kicked out of the tread marks. And so eventually the ground becomes cleaner and cleaner and cleaner. And so you'd expect your resuspension factors to drop over time. And then we have other ones that are another condition that is related to pedestrians moving on fresh contamination. So the sensors, we've identified some concerns with the limitation of these sensors. And so we're trying to figure out how to use a combination of sensors to work around those limitations. And the field experiments were very useful for us to understand those limitations and how we can configure a better a field plan that we hope to start next summer. So with that, I thank everybody. And if there's time for questions, I'd like to entertain that. Thank you. Otherwise, shots for everyone.
Yeah, Mike, I'm wondering, are you guys doing anything related to the impact of the resuspension on infiltration into the buildings? Because it seems like that's an important question to answer, because they may want to have people shelter in place, but if it's not going to do any good, maybe that's not a good option. And it seems like that's a important part of the whole resuspension question.
Yeah, that's a really good one, Paul. I think the data that will generate from realistic resuspension factors because of pedestrian and vehicle movement will provide information to those modelers. So in certain models then, they are some models are very spatially aware of where the contamination is. So they'll have control volumes of contamination. They'll follow those control volumes around. And so for instance, so they can see when there's a proof of contaminated air that's near an intake. Now, whether they're sophisticated enough to know building intakes, I know that they know there is a particular model that does subway intakes and outflows. And so I know there is an ability to mathematically handle that. Now, whether those models will handle it for the buildings, I'm not sure, but certainly we'll be able to provide resuspension factors that the models can use to know what in say the tens of meter scale, what the concentration of resuspended material might be in a model that's aware of the building and the movement of airs around that. So for instance, the quick model is a building aware model. It tracks packets of air as they move around because of wind patterns and because of the obstruction of buildings. So, and then it's looking at resuspension. Where does the resuspension occur? Okay, if it occurs because it's along an expressway, it can follow those plumes of air around and see where they distribute then. So I don't think I answered your question.
Any other questions for Michael?
Bill's got one.
The cleanup guy, not the rat guy. How does this impact? I mean, in thinking about this, we don't want necessarily responders to go out and hose down everything and wash it into storm sewers and into creeks. But if your tracking makes it go there anyway.
Yeah.
And what we're doing is preventing contamination in buildings. I mean, maybe that should be a recommendation. It's not a wide area cleanup. That's not what we do in wide area cleanup. But as the emergency response, maybe these roadways should be hosed down and prevent it from getting into buildings, preventing people who are being relocated from, ingesting that stuff. It's just a question. Just
Yeah.
a thought.
So, yeah, so that brings up a larger issue. What do you do about it? So there have been suggestions one of the reviewers of our first draft of the paper at Health Physics had mentioned, maybe you should talk about what you would do to mitigate then the hazards associated with the particles, and particularly, can you discuss fixatives? So that's another option. Is maybe what you do is you spray down latex paint. It's not designed to stick outside. It's certainly crummy. It's going to degrade quite quickly. But if that's going to help for the next 48 hours or 96 hours, maybe that's what you do. And then you don't have to deal with the water and the uncontrolled ability or the uncontrolled nature of spraying down with water. But water is another one. Maybe it's not a bad idea if the rain gods brought down a little bit of precipitation. I mean, that's what they do at construction sites. And they become a lot more sophisticated these days, but essentially what they're doing is they're just spraying water down to make it a little bit wet. And that way you don't kick up as much dust. You can spray, you can imagine, say, for instance, street sweepers. Those are designed to just spray a tiny bit of water, not enough water to create runoff. They're generating water so that when they're using their scrubbers to pull the twigs and the gravel off the ground, that they're not generating PM10 and PM1 behind it. So maybe something as simple as running street sweepers, a train of street sweepers every several hours during an evacuation. Maybe that would be a solution. I don't know, but yeah, I don't think you want. Yeah. Yep. Every 3 days in Chicago, it rains on average over the year. Every 3 days.